All right, so this video is going to look at applications that can use the ideal gas law in order to determine quantities. Two of those quantities involve molar mass and density. Why do I have an ice cream cone on the screen? That is one way that the ice cream cone is a mnemonic you can use to rearrange the ideal gas law for molar mass. Molar mass represents your grams per moles. And since you can use the ideal gas law to find moles, if you know the mass of your gas and you divide it by the ideal gas law for moles, you would get molar mass. So if I substitute for N in the ideal gas law, G divided by the molar mass, I can rearrange it to get mm, the molar mass, is equal to the mass times the constant times the temperature over the pressure and volume. And so how that relates back to ice cream, M&Ms are great over a pint of vanilla. We can also use that relationship to look at density. You could be given a mass and you could use your ideal gas law to solve for volume and then divide the two. Or if you aren't given a mass, but you are told the identity of your gas, you can rearrange the M&M equation for ideal gas law and solve for density by taking, since mass over volume is our density, we can take that component out of the M&M equation, and density would be equal to the pressure times the molar mass of your gas divided by the constant and its temperature. So with all of that in mind, if you were given a density, you could use that density to calculate molar mass. So in this example, we want to know what the molar mass is of 6.15 grams of an unknown gas that has a volume of 2.500 liters, is at a pressure of 115 kPa, and is at a temperature of 10 degrees Celsius. So if we use that M&M equation, we have our mass, we know our constant, we know our temperature, we can convert that to Kelvin. We have our pressure in kPa, which we can convert to atmospheres, 1.13, and we have our volume, 2.500 liters. So our atmospheres, our liters, and our kelvins will all cancel, and we are left with grams over mole. So when we do the mathematics and we round for sig figs, we get that the molar mass of this unknown gas is 50.6 grams per mole. Again, we can also use this to find density either by being given a mass and calculating volume, or in this case, because we have the identity of the gas, we can use our M&M equation. Density is equal to mass over volume, which is equal to the molar mass of the gas times its pressure over its constant and Kelvin temperature. So the molar mass of ammonia is 17.04 grams. At STP, we are at a pressure of 1 atmosphere and a temperature of 273 Kelvin, and then we have our constant, 0.08206. The atmospheres, the liters, the moles, and the kelvins all cancel. The STP values are defined quantities, so they're not going to affect our sig figs. I went ahead and rounded this to 3. You could have gone out 4 due to the molar mass, but 0.761 grams per liter would be the density of this ammonia gas. So the final example that we're going to look at is going to use molar mass with the ideal gas law to determine a molecular formula of a chemical substance. In this example, our gas has a mass of 556 grams. Its volume is 58.4 liters and its pressure is 758 torr when it's at a temperature of 2.5 degrees Celsius. We want to know what the molecular formula is of our gas if the empirical formula is N2O5. Remember that our molecular formula has to be either the same or a multiple of our empirical formula. We should be able to compare the masses of those two formulas to one another to determine what that ratio would be. So we can use our M&M equation to calculate the molar mass first of our gas, which would be its molecular formula's mass. So we can take the 556 grams, the constant, your temperature converted to Kelvin, your 758 torr converted to atmospheres, and your volume of 58.4 liters. We cancel out all but grams per mole, And when we go ahead and follow through with the math and sig figs, we get that the molar mass of this gas is approximately 216 grams per mole. We can now calculate, or you could have done this at the beginning, the molar mass of our empirical formula, taking 2 nitrogens and 5 oxygens, and that gave me a molar mass of 104.02. Well, if I know that the molecular formula is some multiple of the empirical formula, and I have their 2 respective masses, I should be able to determine the approximate ratio of the molecular formula's composition to the empirical. And in this example, it's roughly 2. So what that tells me is that my molecular formula would have twice the amount of nitrogen and oxygen atoms that are represented in my empirical formula.